Hello, in this video we're going to talk a little bit about geometric sequences. Arguably, linear functions with a constant rate of change are the most important class of functions. And then exponential functions, which have a constant percentage rate of change, are the second most important class of functions. When we restrict the domain of an exponential function to the natural numbers, instead of calling the result an exponential sequence, we call it a geometric sequence. Instead of a common difference between two terms, like we had in linear or arithmetic sequences, we have a common ratio between terms. In other words, instead of adding a constant each time, we multiply each term by a constant, b, to get the successive term. So then b is a sub k divided by a sub k minus 1, and then a sub k is b times a sub k minus 1. So b is the base of the exponential function. It's also this common ratio between successive terms. Because it's the common ratio, a lot of texts use the letter R for ratio for this instead of B. However, I don't particularly like that because I like to reserve the letter R for the periodic relative, in other words, percentage rate. So R is B minus 1. So we will use the letter B for the base for the common ratio, not R. So recursively, we have a sub k equals b times a sub k minus 1. Non-recursively, we have a sub k is a1 times b k minus 1 times. So that's a sub 1 times b to the k minus 1 power. If we were to extend back to allow a zeroth term, which would logically be a sub 1 divided by b, then a sub k is a sub 0 times b to the k. So this all should sound familiar from your study of exponential functions. In fact, when I do linear functions and exponential functions, I actually first introduce them with really arithmetic sequences and geometric sequences, respectively. So let's see if you can do this one yourself here. Create a table, graph, and recursive and explicit formulas for a geometric sequence with initial term 3 and common ratio 2. See if you can do this yourself. Press pause now. Well, it's pretty straightforward. A sub 1 is 3 and b is 2. So if we did a table, of course, the first part of the table is automatic for a sequence. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. It goes on forever. I just wrote out the first 10 terms here. The first one's 3. We multiply by 2 to get 6. 6 times 2 is 12. 12 times 2 is 24. Times 2 again is 48. Multiply by 2 again, we get 96. Double it again, it's 192. 384, 768, and 1,536. And of course, usually we just write it this way as leaving off the first part of the table for the inputs and just write our sequences that way. So recursive formula for this geometric sequence is a sub 1 equals 3 and a sub k equals 2 times a sub k minus 1 for k is bigger than 1. Explicit formula, non-recursive, is a sub k equals 3 times 2 to the k minus 1. And here's a graph of, let's see, 3, 6, 7, 8, 9, the 10, same 10 points. So these points right here are graphed here. Of course, I had to do a non-square scale to get it to fit, but you can see that also, as usual, this is isolated dots. And of course, if we were to connect the dots and let the domain be all real numbers, we'd have an extension of this sequence, which we would call an exponential function. Let's try another one. Determine recursive and explicit formulas for a geometric series with common ratio 1/2 and initial term 1,000. Write out the first 10 terms and graph it. Try it yourself. Press pause now. Well, here I used GeoGebra to graph it. I used the sequence command in GeoGebra. And it's coming down like this. This is an exponential decay function restricted to the natural numbers, so it's a geometric series. The first term is 1,000, and the recursion relation is 1/2 of a sub k minus 1 is a sub k for k is bigger than 1. Non-recursively, that's 1,000 times 1/2 to the k minus 1. Or I could rewrite this, 1 to the k minus 1 is 1, 2 to the k minus 1 is just 2 to the k minus 1, and if I multiply top and bottom by 2, I can make the power a little bit simpler there. So it's 2,000 divided by 2 to the k. So 2,000 divided by 2 is the 1,000. Yeah, it actually starts at 1,000. Let me fix that. And then 2, put in k is 2. 2,000 divided by 4 is 500. Put in 3, we get 8. 2,000 divided by 8 is 250, and so forth. So we're just dividing each one by 2, or multiplying by half each time. So that is a geometric pattern, and hopefully I've got those details worked out there. And we get this. You might notice here that this one has a limit, that as we go further and further and further out to the right, this fraction or decimal version, whichever you're looking at, is getting closer and closer to 0. So there I've got it written out in decimal form. I could have also, of course, written it in fraction form as well. Okay, so that gives you a quick introduction to that. Now it's time to do a few homework problems with geometric sequences.